Hello, I am Kia Ramani, and today I'm going to present our work titled Multi-modal Program Inference, a marriage of pre-trained language models and component-based synthesis. Our story begins with very famous characters, Bert, Elmo, and Ernie. As you may have guessed, these names refer to recent neural architectures which are optimized for understanding natural language, one of the gold standards defined in achieving artificial general intelligence. These models, which I will refer to as PTAMs during this talk, are trained on extremely large amounts of text gathered from around the web and from the history of humankind literature. In 2020, OpenAI introduced their state-of-the-art PTM called GPT-3. GPT-3 is trained on 45 terabytes of data and consists of about 175 billion parameters. The GPT-3 model quickly became popular, and it is currently deployed in 300 applications and generates over 4 billion words per day. The API to GPT-3 allows developers to teach the model by showing it a few examples of the desired task and request it to solve similar ones. This technique is known as few-shot learning and enables GPT-3 to handle an extremely diverse set of tasks, from parsing or explaining programs to translation between human languages and even generating recipes from a list of ingredients. But probably the most exciting domain that GPT-3 has shown incredible capacity in is generation of executable code from natural language descriptions. In fact, a few months ago, GitHub launched a new feature named Copilot, which uses a variant of GPT-3 as its backend and assists developers in writing various types of code. For example, here, the developer is writing a description of a parser in English with a few samples, and Copilot automatically generates the corresponding code in Python. But unfortunately, it quickly became apparent that such models still suffer from lack of precision and very often can generate faulty code. This initiated hot debates in Twitterverse that whether it is too soon to rely on such techniques in production setups or not. In fact, we performed our own experiments with GPT-3 to gauge its capacity for generating programs in the domain of regular expressions. Regular expressions, or regexes, can be thought of as concise search patterns with multiple use cases in parsing, verifying, and editing text inputs. Regexes can be constructed using the grammar shown here. The grammar defines a set of terminal symbols and a set of typed operators, which can be applied on existing expressions to generate new regexes in this language. For example, here is a regular expression, its corresponding parse tree, and its description in English that we found on Stack Overflow. This expression consists of three main parts. The first part accepts strings made of at least one digit. The second part accepts either an empty string or a single colon character. And finally, the third part accepts 0 or more digits. When all three parts are concatenated to each other, they accept strings like these, but reject strings like these. Now that we understand what exactly this regular expression is doing, let's see what GPT-3 produces when given the natural language description of this task. As you can see, the candidate is somewhat similar to the desired program. However, it is not exactly correct. Unfortunately, the same issue occurs even when we repeat this query under different input settings. In fact, in the paper, we report only 15% success rate for GPT-3 when applied on two standard benchmark sets consisting of similar regex synthesis tasks. This is especially disappointing when compared to the state-of-the-art regex synthesizer with about 60% success rate on the same benchmarks. So, is this the end of the story? In the paper, we show that the answer is no. As you may have noticed, even though none of GPT-3's candidates in this case are equivalent to the target expression, they still contain valuable information about it. For example, large components of the target expression can be found among GPT-3's candidates. And moreover, these candidates contain information about the types of operators that are used in the target expression. For example, the quant operator, shown as question mark here, which is used in the target program, also appears in many of the candidates. On the other hand, the alter operator, which is not used in the target program, is also not used in any of GPT-3's candidates. Based on observations like these, in this paper, we introduce the NLX program synthesis framework. NLX attempts to combine the strengths of PTMs in handling ambiguous natural language descriptions with a novel program synthesis technique that is capable of producing syntactically and semantically precise code. NLX takes two types of specification for the desired synthesis task, and hence is a multi-modal synthesis framework. This is necessary to overcome the intrinsic ambiguity of natural language descriptions. As the first mode of specification, NLX takes the natural language description of the desired program and runs it through GPT-3 to generate a set of candidate programs. Next, NLX takes a set of input and output examples of the intended program's behaviors, which are then used to guide NLX's synthesis engine toward the target program. We designed NLX in a domain-agnostic fashion, which means that it is not specialized for a particular domain, and it takes the grammar of the desired language as one of its inputs. At the heart of NLX framework, there is a component-based synthesis engine. Component-based synthesis, or CBS, in its simplest form is an enumerative search over the space of expressions that can be constructed using the given grammar. More particularly, the search in CBS is initiated by a set of terms in the language, which is then iteratively expanded by applying the operators in the grammar on terms existing in the previous iteration. Once the desired iteration depth is achieved, the CBS engine executes the candidate expressions on the given examples, and depending on the outcome, returns one of the programs consistent with the user's intent. Not surprisingly, performing effective synthesis in this fashion is very challenging for any non-trivial synthesis task. The first challenge is regarding the set of seed programs, which must contain useful components, but also must be as small as possible in order to keep the later iterations tractable. The next challenge is exponential growth of the size of candidate sets at each iteration, which can happen even when the right set of seed terms are chosen. And finally, choosing the right program after the last iteration is a major challenge. At this point, a very large number of programs may be synthesized, many of which may be consistent with the user's intent. The basic CBS synthesizer has no way of determining which program has a higher chance of matching the user's intent. Interestingly, in NLX framework, we were able to design solutions to each of these challenges solely based on the output of the natural language model. Let's first look at our technique for extracting seed components from GPT-3's candidates. A naive approach would gather all subterms appearing in any of the candidates. However, as we saw earlier, this can seriously hinder the next synthesis phases. In NLX, we utilize the two-stage filtering method to get rid of unnecessary seed terms solely based on the set of GPT-3's candidates. We first eliminate components from the set of seeds that occur infrequently in GPT-3's candidates. For example, here the term digit only appears in one of the candidates. This is clearly because of GPT-3's confusion about the desired task. In NLX, we define probabilistic measures that allow us to eliminate such components from being included in the seed terms. Next, we define a notion of redundancy on GPT-3's subcomponents and only keep components which are not redundant. Given a GPT-3 candidate, we can define the set of all subcomponents appearing in that candidate. We define components in that set to be maximal if they occur more frequently than any of their supercomponents. For example, Here, both digits 0 and 9 always appear in the same format that captures the range of digits from 0 to 9. On the other hand, the range component itself appears in many different forms, a few times with the star operator, a few times with the question mark operator, and a few times with the plus operator. This suggests the PTM's high confidence that this component is useful, but lower confidence on how it should be used in the final program. This indicates that this component is a good candidate to be included in the seed set, so NLX can consider different structures around it while searching for the target program. Having seen how components find their ways into the set of seed terms, let's now look at the iterative expansion strategy used in NLX to overcome the exponential growth of the candidate set. This strategy is called beam search, which enforces that at each iteration step, only a subset of constructed terms are considered for expanding the set of candidate terms in the next iteration. The ultimate goal here is to choose the subset of considered terms wisely, so once the desired iteration depth is achieved, the target program will be found within the beam with a high probability. In NLX, we define probabilistic measures to maximize our success rate given a constant beam size. For example, in order to bias the search according to the distribution of operators in the PTM's candidates, we ensure that operators that are not used very frequently, like alter operator here, are also not applied frequently when constructing the beams either. Moreover, in order to make sure our selection strategy does not flood the state space with semantically equivalent programs, we designed a novel technique, which we refer to as semantic condensation. The main idea here is that at each iteration, we can run the candidate programs on the given examples, and depending on their output, classify them into semantic equivalence classes. We can then apply our selection method on each class separately and choose a subset according to the size of that class. This way, we can ensure high semantical diversity within the chosen candidate programs. We have shown in the paper that semantic condensation positively affects the overall performance of the NLX framework. Lastly, let's talk about the ranking of the consistent programs which are found at the final iteration phase in our approach. Here, once again, we use the candidates from the PTM to rank programs that are consistent with the user's intent. In particular, we apply two measures of distance, which we empirically found to give us the best performance. The first measure is the Euclidean distance between operator vectors of the programs, and the second measure is the Levenshtein distance between the string representations of them. The Levenshtein distance is defined as the number of single location changes that must be performed to transform a string into another string. For example, in this case, among these four synthesized programs, all of which are consistent with the given examples, the closest one to the PTM's output according to these measures is in fact the target programmer, and hence the synthesis in this case is successfully completed. Before I finish this talk, I'm going to present our empirical experiments with NLX. We evaluated NLX using two standard benchmarks consisting of 150 synthesis tasks similar to our running example. We compared NLX to three baselines: the state-of-the-art regex synthesizer named Regel, shown as the purple bar, and two other baselines, which we defined to be the GPT-3 when it is used as an end-to-end synthesizer, shown as the green bar, and a naive brute force version of NLX, shown as blue bar. We show in the paper that NLX outperforms all three baselines by at least 20%. Please download our paper, where you can find more about our experiments, including an ablation study, showing the effectiveness of each of the NLX's components and its application on another domain, namely the domain of CSS selectors. You can also read more about our techniques for optimized use of the PTM based on ideas from information retrieval literature. To recap, in this paper, we show that pre-trained language models can be thought of as gateways to fully automated program synthesis from natural language descriptions. We propose multimodality as an effective method for overcoming the intrinsic ambiguity in natural language descriptions and present the NLX synthesis framework. We designed NLX in a domain-agnostic fashion and instantiated it in two programming domains, the domain of regular expressions and the domain of CSS selectors. We believe NLX points to a promising direction for future work, where it can be instantiated in many more domains, including larger and more general-purpose programming domains. At the end, I would like to thank the amazing members of the pros team at Microsoft, especially my mentor, Dr. Muhammad Raza, who worked very hard to make this project possible. Thank you very much for your attention.